Today I start on important topics related to linear algebra. Especially we use vector space, and obviously we that means discuss vector space in previous class, and obviously this vector space plays important role in linear algebra, especially algebra. Okay, so we construct this vector space, and today we discuss so many examples of vector spaces. Okay, we start from that means we also discussed so many examples in previous class. Today I start from some that means function. Okay, we start from example function. Let fx equal to what? A n x to the power n, a n minus 1 x to the power n minus 1 dot 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 a1 x plus a0, and what? And gx equal to bm x to the power m, bm minus 1 x to the power m minus 1 dot 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 b1 x plus b0. Okay, be polynomial with coefficient from a field f. Be polynomial with coefficient from a field f. Okay, with coefficients from a field f. Okay, then what happened? Then we talk about that. Suppose that m less than equal to n, then what happened? Then obviously we that means define. Okay, define what? Define b n m plus 1 bm plus 2 dot 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 bn equal to 0. Okay, then gx can be written as okay, written as what? Then gx can be written as what? Okay, here we write about that gx equal to bn x to the power n, bn minus 1 x to the power n minus 1, and plus dot 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 here b1 x plus b0. Okay, that means we define this one. Then what happened? Then obviously fx plus gx equal to something, and then we also define fx plus gx equal to what? Fx plus gx equal to, in this way, an plus bn x to the power n, an minus 1 plus bn minus 1 x to the power n minus 1 plus a1 plus b1 x plus a0 plus b0. Okay, then what happened? Then obviously here we write c belongs to f, and c of fx equal to what? C of an x to the power n. Here c of an minus 1 x to the power n minus 1 dot 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 c of a1 x plus c of a0. Okay, then what happened? Then the set of all polynomials with coefficient from f. The set of all polynomials. Okay, with coefficient from field f. Okay, from field f obviously is a vector space. Okay, is a vector space and denoted by which denoted by what? Which denoted by pf. Okay, understood? I think all are understood that. Then we also discuss on important example of vector space, that means the set of all polynomials from a vector space with respect to addition and scalar multiplication. Now we're going to discussion of another example. We'll erase that portion and going to further discussion of that. Okay. So we obviously taught vector space and obviously so many related examples of vector space. How this vector space work we, that means, handle later, but today we discuss another example. Okay, another example, because if we study this examples then we are also familiar with this vector space. Okay, so we'll also talk about now, let f be any field. Okay, f be any field and a sequence in f, a sequence in f is a function, sigma from the positive integer into f, from the positive integers into f. Okay, then what happened? Then the sequence sigma such that sigma n equal to an, okay, for n equal to 1 2, for n equal to 1 2 dot, okay, and is denoted by an. Okay, then what happened? Let V consist all sequence an in f. Let V consist of all sequences, okay, an in f. What happened? That have only a finite number of non-zero terms, that have only a finite number of non-zero terms an. Then what happened? V consists of all sequences an in f that have only a finite number of non-zero terms an, and f field is sequence, obviously f from the positive integers into f, the sequence sigma such that sigma is equal to an. In this well defined, and we also talk about this V consists of all sequence that have only a finite number of non-zero terms in. Okay, then what happened? If an and bn, if an and bn are in V, if an and bn are in V, then what happened? And t belongs to f, and t belongs to f, define what? Define this an plus bn equal to an plus bn, and tan equal to here tan. Okay, with these operations P be a vector space with the above operation, okay, with the above operations, what happened? V be a vector space. Okay, V be a vector space. So we also discuss two examples of vector space. First is, that means, set of all polynomials with coefficient from a, obviously from vector space, and second is V consists of all sequence an in F that have only a finite number of non-zero terms an. Okay, then obviously V be a vector space, okay, over F. So we erase that portion and going to one discussion of another example which does not satisfy vector space. Okay, one example which that means set is not a vector space. We erase that portion and going to further discussion of that. Okay, we also give some examples of vector space. You also known about it and obviously understood that examples proper in a proper way. Now we're going to further discussion of one not vector space. Okay, that means we discuss this one. Let is equal to what? Is equal to a1 a2. Okay, where a1 a2 belongs to R. Okay, and then what happened? Then for a1 a2 and b1 b2 belongs to S and C belongs to R. Okay, define what? Define a1 a2 plus b1 b2 equal to what? Equal to a1 plus b1 and a2 plus b2. Okay, sorry, a2 difference b2. Okay, and what? And C of a1 a2 equal to what? C a1 C a2. Okay, then what happened? Then obviously S is not a vector space with respect to these operations. Then S is not a vector space with respect to these operations. Okay, understood or not? I think all are understood that problem. Okay, so why this one is not happen also discuss today. Okay, was just one important discussion related to that topics. That means we write it here. A1 A2 plus B1 B2 equal to what? Equal to A1 plus B1 and A2 difference B2. Okay, and again we change this order. B1 B2 plus A1 A2. Then what happened? Then here B1 A1 and here B2 difference A2. Okay, this one are not equal. So what happened? So we talk about that addition is not commutative. Addition is not commutative. Okay, addition is not commutative, so this one is not hold. That means this one be not a vector space. Understood? This one is too easy problem, obviously understood by all, and obviously we discuss it too simple way. Okay, so not a problem at all. We'll erase that portion and going to further discussion of that. Okay, so what happened here? We write it another example. Let is what? Is B is equal to this one. A1 A2. Here A1 A2 belongs to R. Okay, then what happened? Then for A1 A2 and B1 B2 belongs to S, b1 b2 belongs to S, okay, and C belongs to R, and C belongs to R. Define what? Define a1 a2 plus b1 b2 equal to what? Equal to a1 plus b1 0, and C of a1 a2 equal to what? Or C belongs to F. Oh sorry, R is given, okay, so not needed. And C of a1 a2 equal to what? C a1 0, okay. So in this way we define addition and scalar multiplication. So what happened? So what happened here? We also talk about that now, okay. So we're also going to discussion of that. That means here some, that means this one is not a vector space. Why this one is not a vector space, we also discuss today, okay. That means then S is not a vector space. That means this one is not a vector space. So with these operations, with these operations, okay, then what happened? Then obviously we talk about here, that means which conditions is not satisfied, okay. Then obviously if we discuss about that, that means 1 multiplied by a1 a2, since 1 is identity, equal to what? Equal to a1 0, not equal to a1 a2. This one condition is not hold, not satisfied, okay. And another condition is which one is not satisfied, we discuss now, okay. That means in this way we talk about that here a1 a2, okay, plus b1 b2 equal to what? Equal to a1 plus b1 0. But we need this one, we need what? We need a1 a2. A1, sorry, we write it here, we write a1 a2 when this one is happen, okay. When this one is happen, we talk about that when this one is happen. That means b2 is arbitrary, not a problem at all. A2 can't be happen, that means this not equal to a2. That means we can't find any additive identity, we can't find here additive, that multiplicative identity. And here we also, then some addition, some portion we added to here, then how we get a1 a2? This can't be possible. That means this not equal to a1 a2 in any way, okay. So that means we not obtain this one, understood? That means b1, this implies that b1 equal to 0, not a problem at all. But b2 can't express in any way where we obtain 0, that means here 0, so a2 is can't possible by this way. So here identity is not, that means evaluated by these operations. So this is not a vector space with these operations, okay. So understood, I think. Next we also discuss one important, that means cancellation law for vector addition, we also discuss today, okay. So it is that portion and going to further discussion of that, okay. We also known about that cancellation law for vector addition, okay. So we write it here, cancellation law for vector addition, cancellation law for vector addition, okay. Cancellation law for vector addition, also discuss it now. if xy and z are vectors okay, in a vector space V, in a vector space V, okay, such that what, such that x plus z equal to y plus z, then what happen, then x equal to y. Okay, so how we write this one, that means we also write proof of that, how we obtain this result, we write proof of that here. Okay, there exists a vector v, in V, okay, such that what, such that here z plus v equal to 0. Okay, then what happened, thus in this way we write, thus x equal to x plus 0 equal to x plus z plus v, okay, equal to what, x plus z plus v, okay, equal to what, x plus z equal to y plus z plus v, equal to what, equal to, here we write y plus z plus v, equal to what, equal to y plus 0 equal to y. Okay, so what happened is here x equal to y. Okay, we obtain this one, that means x plus z and y plus z equal, implies that x equal to y. Cancellation law for vector addition, this one is too easy and we also discuss in a simple way. Okay, so not a problem at all. We also going to further discussion, okay, further discussion of that, that means the vector 0 described, the vector 0 is unique obviously, and now obviously we also discuss the vector in the vector addition inverse, vector addition identity are unique. Okay, so we also discuss another important theorem related to that. Okay, well, it is that portion and going to further discussion of that. So we now study more and discuss an important topics now. Okay, this is too easy, but obviously we have to know that. Okay, in any vector space V, the following statements are true. The following statements are true. Okay, the following statements are true. What we write it here? What? First, 0x equal to 0 for each x belongs to V. For each x belongs to V. B, what happened? Minus ax equal to what? Minus of ax. Okay, equal to a into minus of x. Okay, for each a belongs to, if and each x belongs to V, and each x belongs to V. Okay, C, what happened? C equal to a0 equal to 0 for each a belongs to a. Okay, so we discuss it now. we discuss this topics now. Proof of part A. What happened? We write it 0x plus 0x equal to what? 0 plus 0x equal to what? 0x equal to what? Equal to 0x plus 0 equal to what? Equal to 0 plus 0x. Okay, hence what happened? Hence 0x equal to 0. Understood? Next we discuss it B. The vector minus ax equal to what? Is the unique element of V. Is the unique element of V. Okay, such that what? Such that ax plus minus of ax equal to what? 0. And thus if ax plus minus ax equal to what? Equal to a plus minus ax. Okay, equal to 0x equal to 0. Understood? Then what happened? Then here we write minus, this implies that minus ax equal to here minus of ax. Okay, understood? Not a problem at all. Then we also going to further discussion of that. What discussion? We erase that above portion and going to further discussion of that. Here we write it in this way: a multiplied by minus x equal to a minus 1x equal to what? Equal to a here minus 1x equal to what? Equal to minus ax. Okay, then what happened? Then we write it a multiplied by minus x equal to minus ax equal to minus of ax. Okay, understood? I think all are understood that portion clearly. Not a problem at all. And now we're going to last portion C. Okay, C is what? Is given that a0 equal to 0. We have to prove this one. Okay, that means how we that means going to further discussion of that. Okay, a multiplied by 0 equal to 0. That means a times 0. Okay, a times 0 multiplication. Okay, then this one is, we know about that. What? We know about that 1 multiplied by 0 equal to 0. Since 1 is multiplication identity. Okay, and in this way we write it a is multiplied by 0 equal to 1 multiplied by 0, 1 multiplied by 0, dot dot dot, 1 multiplied by 0. Here a times. I understand? I think all I understand about that. Then this one is what? This one is equal to 0 0 0 a times. Then this one is what? This one equal to 0. Understood? Not a problem at all. We clearly discussed this one. If a is greater than 0, then this one is happen. If a is less than 0, then what? Then means what is needed is here. If a is less than 0, if here we write a greater than 0, then this one is possible. Okay, if a less than 0, then what happen? If a greater than 0, if a less than 0, then what happen? Then we also discuss this one. A multiplied by 0 equal to what? That means minus b multiplied by 0 equal to minus of b0. Okay, and obviously b greater than 0. then b0 equal to minus of 0 equal to 0. Okay, because from earlier portions b0 equal to 0, so not a problem at all. If b belongs to f, we done this one is clearly. Okay, so another one we discuss today, so that means one example related to polynomial. Okay, so we erase that portion and going to further discussion of that. What happened is here, if f and g are polynomial of degree n, if f and g be polynomial of degree n, be polynomial of degree n, okay, then what happened? Then fg, then f plus g be a polynomial of degree n, be a polynomial of degree n. Okay, how this one is happen, this one is true or false, we discuss today. Okay, we also discuss this one is false. How this one is false, this one is too easy problem. We write it here, a equal to n x to the power n minus 1 x to the power n minus 1 plus dot dot a1 x plus a0, and here gx equal to, we write it in this way, minus an x to the power n plus dot 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 an minus dot dot dot. Okay, in this way here a0 dash. Okay, then what happened, fx plus gx equal to what, fx plus gx equal to an minus 1 dot x to the power n minus 1 dot 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 a0 plus a0 dot. Then what happened, this one is polynomial of what, polynomial of degree n minus 1, and this one's are polynomial of what, polynomial of degree n. Okay, so not a problem at all. That means f plus g can't be polynomial of degree n. Okay, so this one is an important example we also discussed today, and obviously familiar discussion we do in this way. Okay, we also discussed familiar examples. We also know about some even functions and odd functions. Today we discuss about that, so we write it here. Which function is called even functions? A real valued functions, a real valued function if, a real valued functions if defined on the real line, defined on the real line, okay, is called an even function, is called an even function, is called an even function if what, f of minus t equal to f of t for each real number t, for each t belongs to R. Okay, then what happened, then we see about that, the set of all even function defined on the real line with operations of addition and scalar multiplications obviously be a vector space. How we discuss this one, that means we also discuss vector space B, obviously set of those functions satisfies these properties. Okay, then obviously we talk about that here t belongs to R. Okay, we talk about that this is a vector space. How this one is vector space we also discussed today, f plus g equal to, similar way g plus f, not a problem at all. Okay, in this way we also discuss this one, that means this the set of all functions, set of all even functions. Okay, that means this one, if we talk about f is, that means 0, then this one is, that means this one obviously not a problem at all. We also discuss in this way. Okay, too easily we also discuss in this way, that means a plus 0 equal to f, and in this way we also done everything, and 1 multiplied by f equal to f, and so this one are satisfied these conditions. Which condition? Then this one be a vector space with respect to addition and scalar then scalar multiplication. Okay, so we talk about in this way, which that means fx plus gx equal to, okay, fx f plus g x equal to fx plus gx, and if alpha fx equal to alpha f of x. Okay, not a problem at all. In this way we also discuss what, discuss this one, that means be a vector space, be a vector space. Okay, be a vector space. Now we are also going to further discussion of that. Also that means also learn even odd functions in this way, but today we'll stop here, not discussion more. So we learned so many topics related to vector space, and if you get this type of video, please subscribe my channel, follow this type of video, and also see more and more times to understand this in better way. Okay, so if you gives like, please click on like options. If you have any suggestions, any comments, any questions, write it in comment box. So today I stop here. Thank you.